Welcome to our deep dive today, where we're going to be kind of exploring this book by Manfred Spitzer, "The Mind Within the Net: Models of Learning, Thinking, and Acting." Um, and he uses this really fascinating analogy, and it's kind of comparing the brain to computer neural networks. So just imagine gaining a deeper understanding of psychology, psychiatry, even child development, through the lens of computer science, and that's kind of what we're going to be talking about today. Just to give you a little bit of a taste of what's in store for today, we'll be uncovering some mind-blowing facts, like how our brains are actually constantly changing, creating new neurons. You'll learn about the just incredible number of connections in the brain, even more than the stars in our galaxy. And we'll debunk the myth that faster learning is always better. Sometimes slow is the brain's secret weapon. Plus, we'll even tackle the mystery of phantom limbs. How can you feel something that's no longer there?
It's amazing how Spitzer really bridges these seemingly like separate fields by looking at, the brain and its complexities and then applying the principles of computer science. It just opens up a whole new way of thinking about how we learn, process information, interact with the world.
It's so intriguing. I mean, we often marvel at the speed and power of computers, but Spitzer actually points out that computers, for all their speed, can be surprisingly unreliable compared to the human brain.
Yeah, and so you see, individual neurons are actually a lot slower than the transistors that you find in a computer chip. But their strength really lies in their sheer number and that intricate way that they connect and they communicate. It allows the brain to process information in this massively parallel fashion, a feat that still really challenges even the most advanced computers. I mean, just think about it. A single error in a computer program can bring the whole system crashing down. Like that infamous Pentium chip flaw that forced a massive recall back in the 90s. But the brain, on the other hand, is really built for resilience. Even if some neurons fail, the network as a whole can compensate and keep functioning.
It's almost like comparing a highly specialized, super-fast solo performer to a vast interconnected orchestra. Individually, the musicians might not play as fast, but the symphony that they create together is far more robust and nuanced.
Yeah, that's a great analogy. It really captures the essence of the brain's distributed processing power. And this interconnectedness is what makes the brain so incredibly good at things like pattern recognition, something that computers, they still struggle to master.
Oh, it's so true. I mean, have you ever stopped to think about how effortlessly you can recognize a friend's face in a crowd, even with changing lighting, hairstyles? Computers need complex algorithms and tons of processing power for that, but our brains do it in an instant.
And that brings us to the heart of Spitzer's argument about learning. He challenges the notion that learning is simply about storing information like data on a hard drive. Instead, he emphasizes the importance of modifying the strength of connections between neurons. This is a process known as long-term potentiation, or LTP.
LTP. The brain's way of solidifying memories and learning from experiences. I remember reading about how Spitzer breaks down LTP into three key aspects: cooperativity, associativity, and specificity.
Yeah, and let's start with cooperativity. This refers to the phenomenon where multiple neurons firing together strengthen their connections, and it makes it easier for them to fire together in the future. It's like teamwork on a neural level, where repeated activation of a group of neurons makes their bond even stronger.
Then there's associativity, where the brain links different stimuli together. I remember reading about a study where researchers paired a tone with a puff of air to a rabbit's eye. And after repeated pairings, the rabbit would blink even when it just heard the tone alone, showing that its brain had learned to associate the two stimuli.
It's a classic example of how associativity works, and we experience it every day. I mean, it's how we learn to avoid things that have caused us pain or discomfort. For example, you probably wouldn't touch a hot stove twice because your brain has formed a strong association between the sight of the stove and the feeling of pain.
And lastly, there's specificity, which means that changes happen to specific synapses, the connection points between neurons. It's like targeted learning, where the brain strengthens the connections that are relevant to a particular experience.
Exactly. And this brings us to another intriguing point that Spitzer raises, and it's the significance of slow learning.
You would think that faster learning is always better, right? But Spitzer makes a compelling argument for why sometimes slow and steady wins the race, especially when it comes to deeper understanding and knowledge retention. It seems counterintuitive, but think about it. Cramming for an exam might help you pass the test, but you probably won't remember much of the information a week later.
Exactly. Spitzer even uses mathematical proofs to illustrate this point. He argues that slower learning allows the brain to extract general principles from experience rather than just memorizing isolated facts. It's like building a solid foundation for a house, brick by brick, rather than just throwing up flimsy walls that could crumble at any moment. Slow learning might take longer, but the knowledge you gain is more robust and applicable to a wider range of situations.
So the next time I'm feeling frustrated that I'm not grasping a new concept as quickly as I'd like, I'll try to remember that my brain might just be taking its time to build those lasting connections, which is ultimately a good thing.
Absolutely. It's about quality over quantity when it comes to learning. And this leads us to another fascinating aspect of how the brain handles information: its remarkable ability to abstract and compress data efficiently. A concept that Spitzer refers to as vectors in the head.
Vectors. Now that sounds a little intimidating. We're not talking about complex geometry here, are we?
No, not exactly. Think of it this way. Imagine you're trying to describe a friend's face to someone who's never met them. You wouldn't list every single detail, right? You'd probably focus on their key features, their eye shape, their nose size, hair color, things like that. Those are like the vectors in the brain, the essential pieces of information that capture the essence of something without getting bogged down in unnecessary details.
So it's like a mental shorthand,
Yeah,
a way for the brain to store vast amounts of information in a compact and efficient way.
that's exactly right. And this vector coding, it applies to much more than just facial recognition. It's how our brains represent everything from colors and shapes to complex movements.
Wow, it's amazing how the brain can take all this raw sensory input and distill it down to these essential features. It's like having a built-in filter that helps us focus on what's important. But how do these vectors in the head actually work? Like, how does the brain create them and use them to represent the world?
To understand that, we need to delve into some groundbreaking research, particularly the work of Apostolos Georgopoulos, who studied direction-sensitive neurons in monkeys. Now, this might seem like a leap, going from abstract vectors to monkeys moving livers, but bear with me. Georgopoulos' research provides incredible insight into how these vectors are formed and used.
Okay, I'm intrigued. Monkeys and neural networks. This deep dive is taking us on quite a ride. Tell me more.
What Georgopoulos did was incredibly clever. He trained monkeys to move a lever in different directions while simultaneously recording the activity of neurons in their motor cortex, the part of the brain responsible for planning and executing movements.
So he was essentially eavesdropping on the brain's conversations as the monkeys were moving their arms.
That's a great way to put it. And what he discovered was remarkable. Certain neurons fired more strongly when the monkey moved the lever in specific directions. So you could think of it as some neurons being tuned to movement towards the left, others to movement towards the right, and so on.
So it's like each neuron had its own preferred direction, its own little vote for which way the lever should move.
Exactly. But what's truly fascinating is that Georgopoulos found that the brain doesn't rely on single neurons to encode direction. Instead, it represents the intended direction of movement as a population vector. This means that the direction isn't determined by one neuron shouting the loudest, but by the combined activity of many neurons, each contributing a small vote for their preferred direction.
So it's more like a democratic system in the brain where the direction is decided by a majority vote from a whole population of neurons.
That's a fantastic way to visualize it. And by analyzing the pattern of activity across this population of neurons, Georgopoulos could accurately predict the monkey's intended movement even before the movement actually took place.
That's mind-blowing. It means that even our intentions, our thoughts about movement, are represented as these vectors in the brain. So how does this concept of population vectors relate to the broader idea of vectors in the head?
It's a great question. Georgopoulos' work showed us how the brain uses vectors to represent something as specific as a direction of movement. But the principle applies more broadly. Instead of storing every minute detail of what we perceive or intend to do, our brains create these streamlined representations, these vectors that capture the essential features. Think about color perception, for example. Instead of remembering every single shade of red you've ever seen, your brain probably has a vector representing the general concept of redness, encoding the essential qualities that make something red.
This is so fascinating. It's making me rethink how I perceive the world around me. I'm starting to see everything as a collection of these vectors, these mental shorthand notes that my brain uses to navigate reality.
And that's just the tip of the iceberg. These vectors play a vital role in how we learn, remember, and make decisions. But to understand that, we need to explore another remarkable feature of the brain: its ability to deal with missing information, to adapt and rewire itself in the face of change. And that brings us to the intriguing and sometimes perplexing phenomenon of phantom limbs.
Now, that's something I've always found both fascinating and a little bit spooky. How can someone feel sensations in a limb that's no longer there? It seems like a glitch in the system, a phantom in the machine, so to speak.
It might seem like a glitch, but it's actually a testament to the brain's incredible plasticity, its ability to rewire itself in response to new experiences and challenges. Spitzer tackles this mystery by explaining the concept of deferentation.
Deferentation. That sounds a little intense. What exactly does it mean?
Essentially, it means that the brain is no longer receiving sensory input from a particular body part, such as when a limb is amputated.
So it's like the brain is suddenly cut off from its usual source of information. No wonder it would lead to some strange sensations.
Precisely. And this lack of input triggers a cascade of changes in the brain. The area that used to receive signals from the missing limb doesn't just sit idle. It starts to receive input from neighboring areas, such as the face or the remaining stump.
So it's like the brain is trying to compensate for the missing input by rerouting signals from other areas. But how does that explain the specific sensations that people with phantom limbs experience?
Well, remember how we talked about the brain's somatosensory map, the representation of the body on the surface of the brain? When a limb is lost, the corresponding area on this map becomes deprived of its usual input.
Right, so there's this blank spot on the map where the missing limb used to be represented.
Exactly. And this blank spot doesn't stay blank for long. The brain, being the efficient machine that it is, starts to reorganize. The areas surrounding the blank spot start to encroach, taking over that unused territory.
So the face area is right next to the hand area on the brain map. It might start to take over the hand area when the hand is no longer there.
Precisely. And this explains why some people with phantom limbs report feeling sensations in their missing hand when their face is touched. The brain is essentially misinterpreting those signals because of this reorganization. It's receiving touch input from the face, but because that area of the brain map is now associated with the missing hand, it interprets the sensation as coming from the phantom limb.
Wow, that's incredible. So it's like the brain is creating a new map, a new representation of the body based on the available input. But this still doesn't fully explain why phantom sensations can be so vivid and persistent, does it?
You're right. There's more to the story than just simple rewiring. Spitzer delves deeper into this mystery by highlighting another crucial factor, the role of noise in the system.
Noise. Like the static on a radio. What does noise have to do with phantom limbs?
It might seem counterintuitive, but noise actually plays a crucial role in shaping our brains and our perceptions. In the context of phantom limbs, noise can amplify and distort the signals coming from those reorganized areas of the brain, creating the vivid and sometimes bizarre sensations that people experience.
So noise is actually adding to the phantom limb experience. I would have thought it would make things less clear, more muddled.
It can certainly do that. But noise can also have the opposite effect. It can amplify weak signals, making them more noticeable. Imagine you're trying to hear a whisper in a noisy room. If the noise level is just right, it can actually make the whisper easier to hear. This is known as stochastic resonance.
So noise can act like a sort of amplifier, boosting those faint signals from the reorganized areas of the brain, making them more salient, even if they're being misinterpreted as coming from the missing limb.
That's exactly right. And this noise-driven amplification might be one of the reasons why phantom limb sensations can be so persistent and difficult to ignore. It's like the brain is constantly reminding itself of the missing limb, even though it's no longer receiving direct sensory input.
So even in the absence of a limb, the brain is still actively generating sensations, creating this virtual reality experience based on a combination of rewiring and noise.
That's a great way to put it. The brain is constantly trying to make sense of the world, to create a coherent model of reality, even when faced with incomplete or conflicting information. And phantom limbs are a fascinating example of how this process can sometimes lead to unexpected and even paradoxical results.
This is all so mind-boggling. I'm starting to see that the brain is far more complex and dynamic than I ever imagined.
And we've only just begun to scratch the surface. Spitzer's book takes us on a much deeper dive into these complexities, exploring how these principles apply to a wide range of phenomena, from learning and memory to language and even consciousness.
This is definitely making me want to dig deeper into Spitzer's book. But before we move on, I'm curious to learn more about this concept of noise. You mentioned that it plays a role in shaping our brains and our perceptions. Could you elaborate on that a little bit?
Of course. Noise in a neural context refers to the random fluctuations in electrical activity that are always present in the brain. It's like the background hum of the universe, the static that's always there, even when things seem quiet. You see, we tend to think of the brain as this perfectly tuned machine where every signal is clear and precise, but in reality, there's a lot of randomness and variability in how neurons fire and communicate.
So it's not as simple as just turning neurons on and off like switches. There's this inherent fuzziness, this randomness that's always present.
Exactly. And for a long time, scientists viewed this noise as a nuisance, something that interfered with the brain's ability to process information accurately. But in recent years, there's been a growing appreciation for the role that noise plays in shaping brain function.
So noise isn't always a bad thing. It can actually be beneficial. How does that work?
It might seem counterintuitive, but noise can actually enhance the brain's ability to detect faint signals and to adapt to changing conditions. Let's go back to that example of hearing a whisper in a noisy room. If the noise level is just right, it can actually boost your ability to detect the whisper. This is known as stochastic resonance.
So noise can act like a sort of amplifier, making those weak signals more noticeable.
Precisely. And this principle applies not just to sensory perception, but also to learning and memory. Remember how we talked about long-term potentiation, the process by which synaptic connections are strengthened? Well, it turns out that a certain level of noise is actually necessary for LTP to occur effectively.
So without a bit of noise, those synaptic connections might not get strong enough to form lasting memories.
That's right. Noise introduces a bit of variability, a bit of randomness into the system, and this variability can actually help nudge those weak signals over the threshold for LTP, making those memories more robust and less likely to fade.
This is all so fascinating. It's making me realize that there's so much more to the brain than meets the eye. It's not just a collection of neurons firing in a predictable way. There's this whole other layer of complexity, this element of randomness and variability that's shaping how we learn, perceive, and interact with the world.
And that's just the tip of the iceberg when it comes to the role of noise in brain function. Spitzer delves into even more fascinating examples, exploring how noise contributes to decision-making, creativity, and even consciousness itself. But we'll save those discussions for another deep dive.
I'm already looking forward to it. This has been an incredible journey so far, and I'm eager to see where it leads us next.
Well, then let's continue our exploration of the mind within the net. Up next, we'll delve into the fascinating world of feedback loops and how they shape our brains and our behavior.
Sounds intriguing. Lead the way. Okay, so we've talked about how the brain processes information, learns, and even adapts to change. But I'm really curious about these feedback loops you mentioned. It sounds like something out of a sci-fi movie. How can the brain be feeding back into itself? What does it even mean?
Well, it's a fascinating concept and not as complicated as it might sound. Imagine a thermostat. It measures the temperature in a room and it turns the heating or cooling system on or off to maintain a desired temperature.
So it's constantly checking and adjusting based on the feedback it's receiving.
Exactly. And the brain works in a similar way. It's constantly receiving feedback from both the external world and from within itself. These feedback loops are essential for everything from, regulating basic bodily functions to shaping our thoughts, emotions, and behaviors.
Can you give me like an example of how a feedback loop might work in the brain?
Sure. Let's consider the simple act of reaching for a cup of coffee. Your brain sends a signal to your muscles to initiate the movement, but as your arm moves, your brain is constantly receiving feedback from your senses, about the position of your hand, the weight of the cup, any obstacles in the way. This feedback allows your brain to fine-tune the movement, ensuring that you smoothly grasp the cup without spilling your coffee.
So it's like a constant conversation between the brain and the body, with each action generating feedback that informs the next action.
That's a great way to put it. And these feedback loops are happening at multiple levels within the brain, from individual neurons to entire brain regions.
You mentioned earlier that Spitzer uses a model called Hopfield networks to explain how feedback loops work in the brain. Can you tell me more about those?
Of course. Hopfield networks are a type of artificial neural network that incorporates feedback loops. They're inspired by the way real neurons connect and communicate, and they're particularly good at modeling certain aspects of brain function like memory and pattern recognition.
So how do Hopfield networks actually work? What makes them special?
The key feature of Hopfield networks is that they can store and retrieve memories in a way that's robust to noise and damage. Imagine you have a photograph that's been partially torn or faded.
So you're missing some of the information.
Right. But if you have enough of the original image intact, you can often still recognize what it is. Your brain can fill in the missing gaps using your knowledge of what photographs typically look like.
So it's like a mental reconstruction process.
Exactly. And Hopfield networks work in a similar way. They can store a memory as a pattern of activity across a group of neurons, and even if some of those neurons are damaged or the input is noisy, the network can often still retrieve the complete memory by using feedback loops to fill in the missing pieces.
That's incredible. So it's like the network is constantly checking and adjusting itself, making sure that the memory is being recalled accurately.
Precisely. And this robustness to noise and damage is one of the reasons why Hopfield networks are such a compelling model for understanding how memories are stored and retrieved in the brain. They capture this idea that our memories are not simply stored in isolated neurons, but are distributed across a network, making them more resilient to damage.
This is making me think about the concept of neuroplasticity, the brain's ability to rewire itself. Does the fact that our brains are constantly receiving feedback and adjusting play a role in neuroplasticity?
Absolutely. Feedback is essential for neuroplasticity. It's what guides the rewiring process, ensuring that the brain adapts in a way that's beneficial. Think about learning a new skill, like playing the piano. As you practice, you're constantly receiving feedback about how your fingers are moving, how the music sounds, whether you're hitting the right notes.
So that feedback is what helps your brain refine those neural connections, making you a better piano player over time.
That's right. The feedback is what tells your brain which connections to strengthen and which ones to weaken, ultimately leading to changes in the structure and function of your brain.
I'm starting to see how these seemingly separate concepts, feedback loops, neuroplasticity, learning, and memory, are all interconnected. It's like a complex web with each thread influencing the others. It's a lot more dynamic than I ever imagined.
Exactly. And Spitzer does a brilliant job of weaving all these threads together, showing how they create this incredibly dynamic and adaptable system. But let's not forget the role of attention in all of this.
Oh, that's right. Attention is crucial for learning, isn't it? You can't
Yes.
learn something if you're not paying attention to it. But how does attention fit into this web of feedback loops and neuroplasticity?
Well, attention acts as a sort of spotlight, focusing our mental resources on what's important and filtering out distractions. It's like a feedback loop in itself, constantly adjusting based on what we're trying to learn or remember.
So if I'm trying to learn a new language, for example, my attention helps my brain prioritize the sounds, words, and grammar rules that are relevant to that language.
Exactly. And this focused attention strengthens the neural connections that are involved in processing that language, making it easier for you to learn and remember.
This is making me think about those times when I've tried to multitask, like checking my phone while having a conversation.
Mm.
It's so clear that my brain isn't really able to focus on both things at once. I end up missing parts of the conversation and not really absorbing what I'm reading on my phone either.
That's a great example of how dividing our attention can actually hinder learning and memory formation. When our attention is scattered, those feedback loops are less effective. It's like trying to listen to a faint radio signal with a lot of static in the background. The message gets lost.
So focus and attention are really key to making those feedback loops work effectively.
Absolutely. And this is where mindfulness practices like meditation can come into play. These practices train us to become more aware of our attention and to focus it more intentionally.
So by strengthening our ability to focus our attention, we can actually enhance the brain's ability to learn, adapt, and create.
That's the idea. And this brings us to another fascinating aspect of feedback loops in the brain, their role in shaping our emotions and our sense of self.
Now, this is getting really interesting. How do feedback loops relate to something as complex as our emotions?
Our emotions are not simply reactions to external events. They're shaped by a complex interplay of feedback loops within the brain, involving regions that process sensory information, memories, and bodily sensations.
Can you give me an example of how this might work?
Sure. Let's say you see a snake in your garden. Your visual system sends a signal to your amygdala, the part of the brain that's involved in processing fear.
So that's the initial trigger for the fear response?
Right. But the amygdala doesn't just trigger the fear response and then sit back and relax. It also sends feedback signals to other parts of the brain, including those involved in processing memories and bodily sensations.
So you might start remembering a time when you were bitten by a snake or saw someone else get bitten, and you might start to feel your heart racing and your palms sweating.
Exactly. And these bodily sensations and memories then feed back into the amygdala, intensifying the fear response.
So it's a self-reinforcing loop. The more you feel afraid, the more your body reacts. And the more your body reacts, the more afraid you feel.
That's right. And this feedback loop can escalate quickly, leading to a full-blown panic attack.
That's a great example of how these feedback loops can sometimes work against us. But can they also work in our favor?
Absolutely. Just as feedback loops can amplify negative emotions, they can also amplify positive ones. Think about a time when you felt really happy and joyful.
Like when I was a kid and my parents took me to Disneyland for the first time.
Perfect example. The joy you felt was likely triggered by a combination of sensory experiences, memories, and social interactions. But as you experienced those feelings of joy, your brain was sending feedback signals that amplified those feelings, making them even more intense and pleasurable.
So those happy memories and positive associations create a positive feedback loop that can actually boost our mood and our overall well-being.
That's right. And this is where practices like gratitude journaling and positive affirmations can be helpful. They can help strengthen those positive feedback loops, making us more resilient to stress and negativity.
This is also fascinating. It's making me realize just how much control we have over our own emotions and our own well-being.
Exactly. We're not just passive victims of our emotions. We can learn to understand these feedback loops and to use them to our advantage, creating a more positive and fulfilling life.
This has been an incredibly insightful deep dive into the world of feedback loops. It's amazing to think that these hidden mechanisms are constantly shaping our thoughts, our emotions, and our actions. It's discovering a whole new operating system running in the background of our lives.
It is quite remarkable, and it highlights the interconnectedness of everything in our brains. We can't separate our thoughts from our emotions, our memories from our perceptions, or our actions from the feedback we receive from the world and from within ourselves.
So it's not just a network of neurons. It's a network of feedback loops, constantly interacting and shaping who we are. I'm curious, though, about this connection you made between feedback loops and our sense of self. That seems like a big leap. How do these loops contribute to something as complex as our identity?
It's a fascinating question and one that's still being explored by neuroscientists and philosophers. But one way to think about it is that our sense of self emerges from the constant feedback we receive about who we are, both from our own internal experiences and from our interactions with the world around us.
So it's like a mirror reflecting back to us who we are.
That's a good analogy. Every time we have an experience, every time we make a decision, every time we interact with another person, we're receiving feedback that shapes our understanding of ourselves.
Can you give me like a concrete example of how this might work?
Sure, let's say you're a child learning to ride a bike. The first few attempts might be wobbly and uncertain. You might fall a few times, and you might feel frustrated.
I definitely remember those scraped knees and bruised egos.
But each time you get back on the bike, each time you pedal a little further without falling, you're receiving feedback that tells you that you're capable, that you're resilient, that you can learn and grow.
So those successes, even the small ones, start to shape my sense of self.
Exactly. And as you master the skill of riding a bike, you might start to see yourself as someone who's adventurous, athletic, or independent. These self-perceptions are not just arbitrary labels. They're built on a foundation of real-world experiences and the feedback you've received from those experiences.
This is making me think about all the different roles I play in my life. Daughter, sister, friend, employee, artist. Each of those roles comes with its own set of feedback loops, shaping how I see myself in relation to others.
Precisely. And the way we integrate all these different feedback loops, all these different facets of ourselves, is what creates our unique and complex sense of identity.
This is also fascinating, but it's also a bit overwhelming. It's like realizing that my sense of self is not this fixed, solid thing. It's constantly being shaped and reshaped by my experiences and the feedback I receive.
That's a very insightful observation, and it highlights the dynamic nature of the human self. We're not static entities. We're constantly evolving, growing, and changing, and our sense of self evolves along with us.
This has been a truly mind-expanding conversation. I'm starting to see the world and myself in a whole new light.
And that's the power of understanding the brain within the net. It reveals the hidden connections and feedback loops that shape our lives, and it empowers us to become more conscious architects of our own experiences and our own identities.
But before we go too deep into existential philosophy, I'm curious to learn more about how these feedback loops play out in more concrete ways. You mentioned earlier that they're essential for regulating basic bodily functions. Can you give me an example of how that works?
Of course. Let's consider the regulation of body temperature, a process that relies heavily on feedback loops. Your body has a set point for its internal temperature, usually around 98.6 degrees Fahrenheit. If your temperature rises above this set point, Your brain receives feedback from sensors throughout your body, signaling that you're getting too hot.
So it's like an internal thermostat, constantly monitoring and adjusting.
Exactly. And in response to this feedback, your brain initiates a series of actions to cool you down. You might start sweating, which helps to dissipate heat through evaporation. Your blood vessels might dilate, allowing more blood to flow to the surface of your skin where it can radiate heat away.
And if your body temperature drops too low, the feedback system works in reverse, triggering shivering and other mechanisms to generate heat.
That's right. It's a constant balancing act, with feedback loops ensuring that your body stays within a narrow range of temperatures that are optimal for survival.
This is making me think about all the other automatic processes that our bodies do without us even having to think about them. Breathing, digestion, heart rate, are those all regulated by feedback loops as well?
Absolutely. Feedback loops are essential for maintaining homeostasis, the state of internal balance that's essential for life. They ensure that our bodies are constantly adjusting to internal and external changes, keeping us alive and functioning.
It's amazing how our bodies are doing all this intricate work behind the scenes without us even being aware of it.
It truly is. And it's a testament to the power and elegance of these feedback systems that have evolved over millions of years to keep us alive and thriving.
This deep dive is really making me appreciate the complexity and interconnectedness of everything in our bodies and our brains.
And we've only just begun to scratch the surface. As we delve deeper into Spitzer's book, we'll discover even more fascinating examples of how feedback loops shape our perceptions, our actions, and even our sense of reality.
Well, then let's continue our exploration. I'm eager to see where these feedback loops lead us next.
Picking up where we left off, these feedback systems aren't just confined to, physical processes like temperature regulation. They extend to higher-level cognitive functions, shaping how we think, learn, and even make decisions.
Yeah, I see where you're going with this. Earlier, we talked about how our brains are like this vast network constantly receiving and processing information. But it's not just a one-way street, is it? It's more like this dynamic dance with information flowing back and forth, refining our understanding and guiding our actions.
Exactly, and one of the most compelling examples of this is the role of feedback in language comprehension. Think about how we make sense of a sentence. We don't just process words in isolation. As we hear each word, our brains are actually making predictions about what's coming next, based on the context and our prior knowledge.
So it's like our brains are constantly filling in the blanks, anticipating what the speaker's going to say next.
That's right. And this prediction process is driven by feedback loops. As we hear each word, our brains generate expectations about the following words. And if those expectations are violated, the brain receives a feedback signal, prompting it to adjust its understanding of the sentence.
So if I hear a sentence like, "the cat sat on the D,"
Yeah.
my brain might predict that the next word is going to be like mat or a chair. But if the sentence continues with keyboard, my brain would have to revise its understanding, wouldn't it?
Precisely. That unexpected word triggers a feedback signal that forces your brain to reevaluate the context and come up with a new interpretation. And these feedback loops are happening at lightning speed, allowing us to make sense of complex language in real time.
This is making me think about those times when I've misunderstood someone because I wasn't paying close attention. Maybe my brain was so busy making its own predictions that it missed some crucial information.
That's a great example of how these feedback loops can sometimes lead us astray. If we're not fully engaged with the incoming information, our brains might fill in the blanks with our own assumptions, leading to misunderstandings.
This makes me appreciate the importance of active listening. It's not enough to just hear the words. We need to be fully present, paying attention to both the verbal and nonverbal cues to ensure that our brains are getting accurate feedback and making accurate predictions.
Absolutely. Active listening is a skill that requires effort and practice, but it's essential for effective communication and for building strong relationships.
This conversation is making me realize just how much work our brains are doing behind the scenes, constantly making predictions, adjusting and refining our understanding of the world based on the feedback we receive.
It truly is a remarkable system, and as we delve deeper into Spitzer's work, we'll discover even more fascinating examples of how these feedback loops shape our thoughts, our emotions, and our behaviors.
Well, I'm ready for another deep dive. Lead the way.
All right, let's shift our focus now to the fascinating interplay between feedback loops and working memory. Remember earlier when we discussed working memory as our mental scratch pad? That ability to hold information in mind for a brief period and manipulate it to solve problems or make decisions.
Yes, I remember that example of trying to remember a phone number long enough to dial it. It's such a vital part of our daily cognitive function.
Precisely. And working memory is not just a passive storage system, it's actively maintained and manipulated through feedback loops involving the frontal lobes, the part of the brain located right behind your forehead.
So the frontal lobes are like the conductor of the working memory orchestra, keeping all the different pieces of information in sync and directing the flow of thought.
That's a brilliant analogy. The frontal lobes play a crucial role in inhibiting distractions, updating information as needed, and switching between different tasks. They act as a control center using feedback loops to keep the right information active and accessible while suppressing irrelevant thoughts and impulses.
This makes me think about those times when I'm trying to focus on a complex task like writing a report or solving a tricky problem. It requires a lot of mental effort to keep all the relevant information in mind and to block out distractions. It's like my frontal lobes are working overtime.
Exactly. And when the frontal lobes are fatigued or compromised, we can experience difficulties with working memory leading to forgetfulness, difficulty concentrating, and impaired decision-making.
This is making me realize just how vital these feedback loops are, not just for learning and memory, but for our overall cognitive function and our ability to navigate the world effectively.
And Spitzer highlights that disruptions in these feedback loops can contribute to a wide range of mental health challenges, such as anxiety and depression.
Yeah, I can see how that might be the case. If those feedback loops are out of whack, it could lead to a cascade of negative thoughts, emotions, and behaviors.
Exactly. In anxiety, for example, there might be an overactive feedback loop between the amygdala, the fear center of the brain, and the prefrontal cortex, the part of the brain involved in planning and decision-making. This could lead to a heightened sense of threat and a tendency to overthink and worry.
So instead of the prefrontal cortex helping to regulate and calm the amygdala's fear response, it might actually be amplifying it, creating this vicious cycle of anxiety.
That's a very insightful observation, and understanding these underlying feedback mechanisms can help us develop more targeted and effective treatments for these conditions.
Wow, this deep dive has been an incredible journey. It's made me realize just how much I took my brain for granted. It's not just this static organ sitting in my head. It's this dynamic, self-organizing system that's constantly receiving feedback, adjusting, and adapting to create my experience of the world.
And that's the beauty of it. The brain is not a finished product. It's constantly evolving and rewiring itself based on the experiences we have, the choices we make, and the information we choose to focus on.
That's both empowering and a bit daunting. It means we have a lot more agency than we might realize. We can choose to cultivate habits, engage in activities, and seek out experiences that strengthen those positive feedback loops and shape our brains in beneficial ways.
Precisely. And by understanding how these feedback loops work, we can become more conscious architects of our own minds and our own lives.
Well, thank you so much for sharing your expertise with us today. This deep dive into the mind within the net has been truly eye-opening. It's given me a whole new perspective on how my brain works, and it's inspired me to keep learning and exploring.
It's been my pleasure. Remember, your brain is a marvel of complexity and adaptability. Keep feeding it with knowledge, keep challenging it with new experiences, and keep exploring the fascinating world within the net.
And to our listeners, thank you so much for joining us on this deep dive. We hope you've enjoyed the journey, and we encourage you to keep exploring the fascinating world within your own minds.